Hello and welcome back to CS103. In this lecture we're going to look at the Lambda Calculus, which is a formal symbolic system for writing down functions, and that's something that we want to do. We also will see that once we've written down those functions, we are able to manipulate the sentences that we've written in order to calculate results. So in other words, the Lambda Calculus is a fully fledged system for doing computation. Let's see what it looks like. So it's a formal system for function definition. Formal systems are things in which we can write down sentences, and those sentences have meaning because of the symbols we use and the order that we write them in. An example of a formal system that you've already seen is the propositional logic, Boolean logic. So in other words, when you write down sentences consisting of propositions and ands, ors and nots, the sentences that you write down, A and B and C for example, that has meaning because of the symbols that you use and the order in which you write them. So that's what a formal system is. The Lambda Calculus is a formal system for function definition. And it was invented by a mathematician called Alonzo Church in the 1930s when the foundations of mathematics were being probed. And you can read more about that in Gödel'sche Bach. But it's now used as a device in computer programming, even though it was invented before computers existed. In the 1960s, it was adapted and used as the basis of a programming language called Lisp, which was one of the early languages used in artificial intelligence. And it's later been used as the basis of a language called Haskell, and I'll be introducing you to that this week. It also finds its way into many other programming languages, including Python. So let's look at functions first. Functions are things that we apply to arguments. So here, functions are written in blue, and the inputs to those functions, which I'm going to call arguments, are going to be written in black. Let's have an example. Let's take the function even, which we apply to an integer as its input. So even of 4 is an example. Now, when I apply a function to an argument, I then expect to get a result, an output. In other words, the function takes in an input, does some calculations, and produces an output, like so. So what do I get if I apply the function even to the input 4? Well, even is a function that returns true if the input is even and false if it's not. So that returns true. The second example, not is a function, takes in an input and it inverts it. So here not of true returns false. Add 3 is a function I've written myself, and I'll show you how to write that function using the Lambda Calculus a little bit later. But let's say we've got a function called add 3. It adds 3 to its input. So if I give it the input 5, it returns the output 8. Length is a function where I feed it not an integer but a string, a sequence of characters. And it tells me how many characters there are in it. So length, if I pass it the input argument Fred as a string, returns me the number 4. Integer is what you might think of as a type checking function. It tells you whether or not the argument is an integer. So you pass it any argument you like, could be a string, could be a Boolean, could be an integer, anything you want, and it will return true if it's an integer or false if not. The identity function is a bit of an odd thing. It simply takes in an argument and returns that argument unchanged. So there you go. There are some simple functions for you. Now, all of these functions have a type. Just as simple objects like for and the string ABC and true and false, they all have a simple type. Functions also have a type. And the type of a function is the type of the input and then an arrow like this to the type of the output. So this is the type of this thing and this is the type of this thing. So even of 4, even is going to be a function that takes in an integer and produces a boolean. So it's of type int to bool. Not, well, takes in a boolean, returns a boolean. So it's bool to bool. Add 3 takes in an integer and returns an integer. So int to int. All easy stuff so far. Length of thread, well, that takes in a string and returns an integer. Now, when we get to integer of ABC, you may remember I said this can be of any type you like. So we've got a special symbol which means any type. It's alpha. So we take in any type, but we return a boolean. So this is of type any type, alpha to boolean. That's what this type of this function is. Now, you'll remember that identity takes in any type of thing you like and returns it unchanged. So therefore it takes in any type and it returns that very same type. So it's of type alpha to alpha. So we've seen here, these are the types of the functions, and we've seen that these functions do computation. How does the lambda calculus work though? Well, let's first of all look at how we write down functions using the lambda calculus, and then secondly we'll see how they compute the results. So here, this is a lambda calculus expression for the function add 3, the function that I showed you earlier. Lambda x, x plus 3. So it's a bit like saying in Python, define a function called add 3 of x and then return x plus 3. This is the body of the function, x plus 3. And this x here is called the bound variable. And this is the whole thing is a function ready to apply to an argument. So we have the bound variable, x, that's the thing that comes after the leftmost lambda. And then we have the body, that's the thing that comes after the dot. When we apply this function to an integer, it returns the value n plus 3. So just like I wrote down add 3 of 5 and that returned 8, I can write down lambda x, x plus 3, applied to 2 gives me 5. So the way that I've explained it, you can see, okay, yeah, I see that. But how does it do it? It does it by rearranging the symbols and then doing an evaluation. So rearranging the symbols first is called beta reduction. Beta reduction is where we take the body, that's this bit here, of the lambda expression, and we write it out again, but with the a will replace x anytime it appears in the body. Let's see some examples. So here, the body of the expression is x plus 2. That's going to be the result of the beta reduction. So we're going to write down x plus 2, but every time we see x, we write 3 instead, because that's the bound variable. So we're going to write this down, but with the variable, the bound variable, replaced with 3. And once we've done that, we can evaluate it. So this is going to produce the result 3 plus 2, and that will then evaluate to 5, like that. So it's in 2 stages. The first stage here, this is the beta reduction. And then the second stage is the evaluation. 2 stages. In this one here, the body is y plus y. The bound variable is y, and the argument is 5. So we're going to write out the body, But wherever we see y, we replace it with 5. And that goes for both instances here. So we're going to write down 5 plus 5 as the evaluation, as the beta reduction, and then we evaluate that to get 10. Similar here, we're going to write down the body, length of S, but with ABC in there instead, and then the lambda disappears. So we get length of ABC, so that's length of S, S is ABC, and then you get 3 as the result. This beast looks strange. Lambda K of K applied to Fred. Well, we just do the procedure that I've described. It's the body with X replaced by A. So the body here, well, that's just K. And I replace K with Fred. So it's just Fred. So this, in fact, lambda KK is in fact the identity function that I spoke about. Finally, here's a more tricky one. Lambda X, lambda Y, X plus Y2. Well, the way to look at this thing is just look at the leftmost lambda. The body is all of this. Everything after the first dot is the body. So we're going to write down the body, lambda Y, X plus Y, but we're going to replace the bound variable, which in this case is X, with 2. So have a think to see if you can work out what this is going to return. It's going to return lambda Y 2 plus Y because X gets replaced by 2. And I can't in fact evaluate this yet because it's still got a lambda in it. I'll show you what we'll do with that in a minute. First of all, let's think about the types of lambda expressions. Lambda expressions are functions just like any other function, so they will have a type. What about lambda x, x plus 2? Well, that's going to take in an integer and it will return an integer. So it's of type int to int, that's easy. Similarly, lambda y, y plus y will also be int to int. Takes in an integer, returns an integer. I should say that in my simple scheme here, all numbers are integers, yeah. And I also assume that less than and more than only apply to integers. So lambda s, length of s, well here s is a string. So therefore this is of type string to int. Lambda k of k, well if you remember I said that we can pass in any variable here, sorry, any type here. So it's of type alpha goes to alpha. Now the final one is a bit tricky. If you remember, I passed in an integer, but I got a function back. So I pass in an integer and I get a function. So I passed in an integer, that's the type of the input here. But what I got back, if you remember, was lambda y 2 plus y. Well, I know the type of that sort of thing. It's exactly the same as this one here. So I passed in an integer and I got a function back, one that takes in an integer and returns an integer. If we've got two arguments to a lambda expression, what are we going to do? Say we want to write a function of two variables. So for example here, this is Pythagoras' theorem. F of xy is the square root of x squared plus y squared. How am I going to do that using lambda expression? The way that I do it is I make a queue of arguments. The queue of arguments are going to be processed one at a time, left to right. So 3 is the first one in the queue here, and then 4 is the next in queue. So they're lining up, ready to be bound to variables, one at a time. And similarly, I line up the lambdas at the front, ready to take the arguments, ready to eat the arguments one at a time. So the first argument is going to be bound to x, and the second argument is going to be bound to y. But we do them one at a time. So let's see how this happens. Firstly, I bind 3 to the value x. So the body is going to be everything from here to here. Lambda y square root x squared plus y squared except I replace x with 3. So that's the first of the beta reductions. The second one is where I take in the 4, because I've still got a lambda here. So now I bind 4 to this lambda here. So I write out the entire body, everything after the dot, but I replace the y with 4, like that. Now I've got no lambdas left, I can evaluate it. That's the final step, and that gives me 5. 3 times 3 is 9, 4 times 4 is 16, square root of that is 5. Finally, we can also pass in functions as arguments to other functions. This is one of the things that makes functional programming really powerful. So in Lisp, there was which was my favorite programming language when I was a PhD student, there is a function called mapcar. It takes in 2 arguments. It takes in a list of items and a function which it then applies to those arguments. So if you pass in the list 1, 2, 3, 4 and the function lambda x dot x squared, it will return you the list 1, 4, 9, 16. In other words, it applies the function to each and every member of the list. So here I'm passing in the function lambda x, x plus 2 as an argument to the function lambda f, f of 3. So this is the thing that's playing the part of the function, and this is playing the part of the argument. So we just do beta reduction like we did before. Lambda f dot, and then this is the body, f3. So I rewrite that, but every time I see f, I put this here instead. So it looks like that. So in other words, lambda x, x plus 2 has replaced 3, and it's now in the position of a function. So now I apply beta reduction as usual. That gives me 3 plus 2 because 3 gets bound to x. And then finally that becomes 5. That looks a bit complicated, but if you do it stepwise, step after step, just obeying the laws of beta reduction, that's what you'll get. So based on all this stuff, I've got some exercises for you so you can check your understanding. So first of all, what I'd like you to do in part 1 is just to write out some functions here as lambda expressions. So all you've got to do is to convert these things. F of x is x plus 5. Convert that into a lambda expression for me. Then what I'd like you to do is to perform beta reduction on the following. You don't need to evaluate them at the end. Just do the beta reduction and see where you get to. So in the first one, for example, you don't have to, well, in fact, in all of them, you don't have to evaluate the expression once you've got it. You just have to write down the expression. In the last couple, you'll have to do 2 rounds of beta reduction until you get to the final expression, because there's 2 lambdas. Then what I'd like you to do is to think about the types of the lambda expressions. For each of these lambda expressions, the ones that you invented yourself and the ones in question 2, tell me what the type is. And then finally, rather a difficult question, I'd like you to try to work out for me what the type of this object is. The type of the expression lambda f, f of 3. So it's a function, so it takes in something and it produces something. So it's of type something to something. The question is, what are those 2 somethings? What is the type of its input and what will the type of its output be?